Light, of course, is the main way we as humans perceive the world around us. It's also the main way that we as astronomers learn about distant objects. The nature and the properties of light are going to be extremely important to us. And the first of these is the speed. So light carries energy away from the sun to Earth to warm us. And the speed at which light propagates is huge. It's about 3 times 10 to the 8th meters per second. This large number makes accurate measurement difficult. First really good measurement was in 1850 by Foucault and Fizeau, though there were earlier, less precise measurements. Now, in a classic experiment in 1670, our old friend Newton made the discovery that the sunlight, white, colorless light from the sun, in fact contains all colors of light. He found a way to split a beam of white light into beams of various colors. He was using a prism. Today we use a diffraction grating. And he conjectured that the nature of light was a stream of particles. Of course, he had all the mechanics know-how to understand a stream of particles. Light moved in straight lines, like particles upon which no forces act, moved at a constant velocity. It seemed a lot like mechanical particle model of light would be likely. This is one of the rare cases where Newton was wrong, because in 1799, only 120 years later, Young observes light waves interfering. So he makes the observation that you can take light and you can construct these interference effects where light waves add and subtract and you get nodes. This interference was a hallmark of wave phenomena, so Newton for once was actually wrong. Light is a wave. But never count Newton out. We'll come back to this point in the next clip. And that same Young, 3 years later, shows that our eyes, while they are extremely accurate in giving directional perspective, so they tell us very precisely which direction light is coming from, that's how we construct our image of the world, are in contrast relatively poor as Fourier analyzers, unlike our ears, which can distinguish a great variety of sounds and hear several simultaneous tones and distinguish them. Our eyes are a very poor Fourier analysis machine. They only are sensitive to the relative intensity of 3 colors, red, green, and blue, and we'll see in a minute what that leads to. What we're going to do is an experiment somewhat similar to what Newton did. So we have here a beam of white light, and we're going to put a diffraction grating in front of it, and the diffraction grating splits the white beam so that the white stripe in the center is somewhat dimmed, and on both sides we find the familiar rainbow structure. And so we see a stripe of red flaring to orange and yellow and green and into blue and violet. And we can see what happens when we put a filter in front of the light. We get red light, and when we feed red light into the diffraction grating, what we see in the spectrum is that the green and the blue are missing. Similarly, when we feed green light into the diffraction grating, the blue and the red are missing and only green light comes in. So the diffraction grating is not coloring the light, it is deflecting whatever green light it gets to that region. Again, putting a blue filter in front of the beam, we see that only the blue remains in the spectrum. The blue filter absorbs the green and the red, the green filter absorbs blue and red, and the red filter absorbs green and blue. These are, it turns out, the primary colors. It has to do with our eyes. Here's what happens when you put a cyan filter in front. A cyan filter absorbs the red light and so lets through the blue and the green. Similarly, if we use a magenta filter absorbs the green, letting through the blue and the red. So what we see as magenta is blue light and red light. There is also, we can put a yellow filter in, and this is important. We see that what we perceive as yellow light is, in fact, light that is missing its blue. The green and the red are present, the blue is absent, and we see yellow. And so if we superpose the yellow and the magenta filters, the yellow filter absorbs the blue, the magenta absorbs the green, and what is left is red. And indeed, superposing those two filters, we get red. If we superpose yellow and cyan, the yellow absorbs the blue, the cyan the red. What's left is the green, and we see that very nicely in this picture. And we can keep playing. We can superpose the cyan and the magenta. The cyan absorbs the red. The magenta absorbs the green. putting them on top of each other, we're going to be left with blue. So this has to do with the way our eyes see colors. The important thing for us to take away here is that a filter that absorbs the blue looks yellow. We cannot distinguish this yellow from the yellow in the spectrum there in between the red and the green that is pure yellow light. We saw that, as Young showed us, light is a wave, and also as Young showed us, our eye, in fact, has 3 color detectors, one sensitive to red light, one sensitive to green light, and one sensitive to blue, and what we perceive as color is merely the relative intensity at which those 3 detectors are excited. So yellow light that excites the red and the green approximately equally, because in the spectrum, yellow light is between red and green, cannot be distinguished from a combination of actual red and green light. And so our eye, unlike our ear, is not a very good Fourier analyzer. So much for biology, but this will be important in understanding some phenomena later. And then, once we know that light is a wave, it's not too shocking that color is a property of the wave. Color turns out to be the frequency of light. Visible light has a frequency of order 10 to the 14 hertz. Even at the rather high speed of light, we can compute the wavelength is pretty short. It's between 400 and 700 nanometers. A nanometer is a billionth of a meter, 10 to the minus 9 meter. And these are the units in which typically we measure the wavelengths of visible light, at least in astronomy. And so 400 nanometers, the shortest wavelengths, visible light is the blue light, as this indicates, and the red end of the spectrum is the longer wavelengths, and the order of the colors in the rainbow is according to their wavelengths, so that violet light, in fact, is at the short end of the spectrum, green is somewhere in the middle, around 550 nanometers is green light, and so on.